Thank you for the introduction and for the invitation to this meeting. Thanks to the organizers for setting this up. So my topic will be canonical quantum gravity, and I was instructed by the organizers to keep this at an overview level. So there will be almost no technical details, but you can find them in various status reports, reviews, and also many books by now. So here's my table of contents. First, I will talk about the classical Hamiltonian formulation of general relativity, because this is our starting point for setting up the quantum rules. Then I will talk about the canonical quantization principles quite in general, for an arbitrary theory, so to say. And then I will come to a particular incarnation or realization of these quantization rules in a theory which is by now called loop quantum gravity. So let's start with the first topic, the initial value formulation or classical Hamiltonian formulation of general relativity. This is a quite old approach and has been applied both in the classical and in the quantum setting. It has a long tradition. In the classical setting, it is used nowadays in order to study gravitational waves, for example. So in order to numerically integrate Einstein's equations to simulate or calculate black hole merger gravitational wave templates and so on and so forth. And in the quantum regime, it has been understood that quantum gravity in the Hamiltonian formulation can be understood as a constrained quantum field theory, and this has been pioneered by these people, among them de Wit and Wheeler, who coined the name Wheeler-de Wit equation, which plays a fundamental role here. The key assumption that we start with is that we are talking about globally hyperbolic spacetimes, so that the initial value formulation is well posed. And that immediately implies a topological restriction on our spacetime, and it can be written as a Cartesian product consisting of a time axis and the spatial manifold, which I call little sigma here. And this means that our spacetime manifold can be foliated into leaves. This is sometimes called the 3+1 split of spacetime into space and time. And one can therefore write the 4 metric or the line element in adapted coordinates adapted to this foliation. And we have here the so-called lapse function. We have a 3 metric on the spatial slices, and we have the so-called shift function, which parameterizes how these leaves of the foliation sit in our 4-dimensional spacetime. And then one does what one usually does in Hamiltonian formulation. One performs a Legendre transformation of for example, the Einstein-Hilbert action to the Hamiltonian formulation. And you find out that because of diffeomorphism invariance of the theory, the Legendre transform is singular, and you have constraints, the so-called scalar or Hamiltonian constraint, and the spatial diffeomorphism constraint. But you do get a description in terms of Poisson brackets and so on and so forth. And you pass from the metric and its time derivative to the 3 metric and its conjugate momentum. So an important concept important role is, of course, played by these constraints here. By the way, these are in these so-called Arnold-Desert Misner coordinates, t and little xa, where a runs from 1 to 3. These are nothing but the temporal, and temporal-spatial components of the Einstein equations. So this is the interpretation of these constraints. So it's quite straightforward in principle. You smear those constraints with test functions, test function consisting of a vector field and a scalar function. And you compute the Poisson brackets and you get the structure. and this is called hypersurface deformation algebroid. So an algebroid is a little bit more complicated and more general than a Lie algebra, because you get dot structure constants like in a Lie algebra, but you get structure functions. The inverse of the 3 metric enters in the right-hand side of the Poisson bracket between two scalar constraints. On the other hand, while this is a little bit more complicated, it's still, the observation is that this encodes in the Hamiltonian formulation the local spacetime diffeomorphism covariance of the theory. And what makes it more complicated is this algebroid generalization of the Lie algebra. So it's sometimes people call it an open algebra. And when you now think about quantization, you want to usually quantize also the Poisson brackets. You want to quantize the Poisson brackets in such a way that functions become operators or operator value distributions, and Poisson brackets turn into commutators. So when you think about quantizing this, you want to turn this into operators and obtain a similar structure here, with, of course, where Planck's constant enters the game. And you want to do this in such a way that this algebra is somehow preserved under quantization. In other words, you want to implement this in an anomaly-free sense. And doing this is a major challenge in the so-called quantum reduction approach to canonical quantum gravity, where you really quantize the constraints and want them to obey the quantum analog of this algebra. So this is the one route to this constraint quantization. Another route is the so-called reduced phase-space quantization. So first of all, the Hamiltonian that is playing here generates time translations, so to say, is totally constrained. It's just a linear combination of the spatial diffeomorphism and the scalar constraint. So it's constrained to vanish. So that's already something very strange. Moreover, these two constraints are the generators of gauge transformations, namely spatial and temporal diffeomorphisms. So they generate motions on the phase space which are not observable. Rather, observables should be invariant under the transformations that are generated by this Hamiltonian. So that is also very strange and sometimes called the problem of time. And in order to cope with this conceptual problem, one introduces this concept of relational Dirac observables. And it turns out that this is in one-to-one correspondence with certain choices of gauge fixing. So we want to extract from this totally constrained language, we want to construct things that one can measure, observables, which are invariant under the unphysical motions that are generated by these constraints. And this can be done, for example, as follows. You split geometry and matter canonical pairs into two sets. So if Q and P are all variables, then capital Q and P is one of these subsets, and X and Y is another subset. And they are called true and gauge degrees of freedom. Then you do the following thing. You just solve the constraints for, let's say, Y, and impose a gauge fixing condition on X. So you fix, as one says, you fix the gauge observables, gauge degrees of freedoms. And you want that the gauge is stable under time, under the unphysical motion that is generated by this constraint, that this fixes the smearing functions T, where T is this compound level labeling the shift function and the lapse function. And then you can, in principle, solve this condition and find out that there's now a non-constrained physical Hamiltonian which drives the evolution of the observable degrees of freedom. So of course, this if you think about general relativity, let's say described by the Einstein-Hilbert action coupled to the standard model, then this can be a highly complicated procedure to how to proceed still in the classical theory, but it is actually feasible if you have sufficient number of scalar fields in the game. Now, how do we now quantize the theory in the Hamiltonian framework? Here are the general principles. So first of all, as already emphasized by Renate, perturbation theory is not really an option because of non-renormalizability. Einstein's theory is background independent. There's no metric that is singled out by Einstein's equations. Continuum theory, we want to really stay in the continuum and do not put discrete structures into the game. We want to apply standard quantum field theory methods for the gravitational field plus matter in 3+1 dimensions. And here we also use this very powerful machinery that is given to us by the people that are performing algebraic quantum field theory. So we work in the language of algebras and expectation value states on such algebras. And one thing we have to generalize or to relax as compared to algebraic quantum field theory is that in algebraic quantum field theory, you fix a background metric, and then you construct an algebra of observables which depend on this background metric. And that allows you to state a very important axiom in algebraic quantum field theory, sometimes called the causality axiom, which says that if you have two regions in your space-time, now space-time meaning a differential manifold plus the background metric G0 here, with respect to which these two regions are disjoint, then the algebras of observables commute. So this is implements causality. Nothing can propagate faster than the speed of light. But of course, when you want to transcribe this to gravity, to quantum gravity, then you have a problem because quantum gravity per se does not single out a metric, at least if you're not working in a perturbative setting. It becomes even an operator, and therefore somehow this notion of causality seems to be something which is fluctuating. So maybe an algebraic version of quantum gravity then is as follows. If you are given a state on your algebra, and the algebra doesn't know anything about any background metric, and you have the following property, namely that the fluctuation of the metric or the metric operator value distribution is small. So you could say that the metric is small, is semi-classical with respect to this given state. And if O and O prime are causally disjoint with respect to this expectation value metric, then show that the commutator of these algebras is small in the sense of expectation values. So the difference between these two frameworks would then be, while both use algebras and states, in the usual setting, we fix a background metric, and here we do not do that. So you have something which I would call quantum locality at most when you are trying to formulate this relative to a state. So how do you construct then A of O? Well, we do this starting from what we call time zero fields. Then you use the Heisenberg evolution with respect to the physical Hamiltonian of these time zero fields. Then you get states on the evolved fields, and then you can try to test this idea. So in a little bit more detail, you start. So to give you a little bit more details and a more concrete setting, you start with a Weil algebra given by Weil elements. For little q and p, if you're working in the quantum reduction approach, where you want to impose the constraints as operators, or on the true observables only if you're working in the classical reduction approach. Then you want to express at either the constraints or the physical Hamiltonian in terms of algebra elements. So this would be now elements in the corresponding Weil algebra. And then you study states on this algebra, which provides you with representations of these algebra elements on a Hilbert space and a vacuum. And of course, there are usually zillions of states in quantum field theory, which are unitarily inequivalent. So you want to select states by the requirement that they behave nicely with respect to the Hamiltonian, the physical Hamiltonian that you have, or that they behave nicely with respect to the constraints that you have. So some physical input is needed here in order to select the good states. In addition, so in the quantum reduction approach, you want that the domain, which is given by the representation applied to the vacuum state, is an invariant domain for the constraint operators, and such that this non-anomalous relation holds. And in the classical reduction approach, you would ask that the representation of the Hamiltonian, the physical Hamiltonian, has self-adjoint extensions. The nice thing in the classical reduction approach is that the Hilbert space is already the so-called physical Hilbert space of physical states. And you could, in principle, go ahead and study the S matrix of corresponding to our Hamiltonian and so on. In the quantum reduction approach, this is much more complicated. You do not have the physical states yet. So this will be generalized zero eigenvectors of all the constraints. You would need to equip the solution space of all the constraints with the new physical inner product. For example, using Gelfand triples, also which a concept which I cannot talk about here in more detail, but there are some ideas. And then you have to construct representations in that physical Hilbert space of gauge invariant observers. So you see here that in the quantum reduction approach, you have much more work to do. And therefore, I will focus for the rest of the talk mostly on the classical reduction approach, which is much simpler. Although we will see that the quantum reduction approach plays a small role in the so-called loop quantum gravity realization of this program. So that is already the last part of my talk. I come now to an even more applied setting, namely the loop quantum gravity realization of this program. So the first thing is that one has to go from matrix to Vielbeine, because you want to couple fermions. And therefore, we are not talking about the three metric anymore, but triads, or more precisely, density-tized triads. Also, as Renata has emphasized in her talk, it is of great advantage to work with connections. And therefore, it was a nice discovery in the mid-80s that to see that it is actually possible to formulate the Hamiltonian formulation of general relativity in terms of connection variables. That comes with a small price, namely that you have an additional Gauss constraint, like in any Young-Mills theory. But in principle now, one is in the language of a Young-Mills theory, just that the Hamiltonian that we are talking about is not the Young-Mills Hamiltonian, but the more complicated one. In any case, such a gauge theory formulation then, of course, suggests to work with a Weil algebra, which is using ideas from the Wilson loop variables. So here, this is the path-ordered exponential of the connection along a one-dimensional path. And this is the exponential of the electric flux of the electric field. We call it the electric field corresponding to a triad. And these are the variables that people in Hamiltonian lattice gauge theory like to use, and which has led, for example, to the Susskind-Kogat Hamiltonian in Young-Mills theory, lattice Young-Mills theory. However, in our setting, these one-dimensional and two-dimensional submanifolds of these three-dimensional manifold sigma are not restricted to a certain lattice or a dual lattice. They are totally arbitrary. Now, an important observation is that in the Gauss constraint and the physical Hamiltonian, it is true that all the terms that appear there, the vacuum contribution, the cosmological contribution, all matter contributions, they couple to this Dreibein. And therefore, it would be nice to have a state on the algebra corresponding to these Weil elements here, which is such that it kills the vacuum. And this simple requirement already fixes a so-called irregular state. I will say what I mean by this on the corresponding Weil algebra of so-called Naunhofer-Thirring type. So that is the first motivation for selecting such a state. The second observation is that the algebra that we are talking about here is such that it is equipped with automorphisms corresponding to Young-Mills gauge transformations and spatial diffeomorphisms called alpha G and alpha phi. And the physical Hamiltonian turns out to be invariant under both automorphisms. So the second state motivation is then to choose a state which is just simply invariant under these automorphisms. This is a concept well known in algebraic quantum field theory. And then it turns out that there exists exactly one state which is invariant. So that is then the motivation for picking that state, picking the corresponding GNS representation, and study its consequences. So here are a list of few results. Let me check how I'm doing on time. Yeah, I'm quite fine. So what we do is we in fact use both quantization strategies. We use the quantum reduction approach to the Gauss constraint, and we use the classical reduction approach to the spatial diffeomorphism and Hamiltonian constraint. And it turns out that the Gauss constraint can be implemented, in fact, as a self-adjoint operator on this corresponding GNS Hilbert space. And one can, in fact, write down a closed formula for all solutions to the quantum Gauss constraint. And these are labeled in terms of spins and gauge invariant intertwiners. If you want Clebsch-Gordon coefficients. And this is known as the so-called spin network basis. The corresponding GNS Hilbert space, I have written down of this formula here before, which looks quite abstract. So it just says what does the vacuum expectation value do to a Weil element? And it turns out that you can translate this into a different presentation of this GNS Hilbert space as an L2 space. An L2 space with respect to a certain diffeomorphism invariant measure on a certain space of generalized or distributional connections. So in fact, we have a Schrödinger representation, if you want. In this representation, it has been possible to write down excitations of the GNS vacuum, which were called coherent states because they saturate the Heisenberg uncertainty bounds on both of these while element variables that I wrote down before. So these here, we call them holonomies and exponentiated fluxes. So they are states which minimize the uncertainty relation for those while operators. And there exists certain ordering of this Hamiltonian, which I never wrote down in this talk, but it's related to the quantum Einstein equations. So there's an operator corresponding to the canonical formulation of the Einstein-Hilbert action, if you want, which is very complicated, but there exists an ordering of this complicated operator such that it has an expectation value with respect to these coherent states which approximate the classical value, but of course contains quantum corrections. So this operator is symmetric. If one can show that it's bounded from below, we can, for example, use the Friedrichs extension to make it self-adjoint. That is something that has not been done yet. And what is maybe most surprising is that I really talk about an operator here, not just a quadratic form. This is something unusual in interacting quantum field theory because there is, in 4 dimensions, it would be nice to have an example of an interacting quantum field theory obeying the Weidmann axioms and so on and so forth, such that the object that you write down is not just a quadratic form, of which you cannot just compute matrix elements, but it can actually define it densely on a domain, so that it maps states in this domain to normalize operators. And this is actually possible here, and why this is possible can be traced back to the fact that this representation corresponding to this state takes the non-perturbative structure of the Hamiltonian quite seriously. So this is far away from a Fock representation, for example, and that has this nice consequence. Furthermore, we can write down objects that are very hard to access in Fock representations. We can write down operators corresponding to lengths, areas, and volumes corresponding to 1, 2, and 3-dimensional submanifolds. And these turn out to have pure point spectrum that scales with the Planck length, the Planck area, and the Planck volume. Having access to an area operator gives us also access to the area of black hole horizons. And this fact has been used in order to define a microscopic notion of black hole entropy, and you use it in order to compute the black hole entropy with the area law. Finally, if one implies this kind of state or an analogous state to a mini superspace truncation of the theory, then you obtain a theory that has been coined loop quantum cosmology, in which there's a big bounce. So the organizers have also asked me to list a few problems or open problems that are still open in this approach. Here are some of them. So while omega is a very natural state from the 2 perspectives that I have given to you, it is not strongly continuous for both these smear test functions, little f and capital F. So at least one of the operators is such that you cannot differentiate. And this leads to quantization ambiguities, lots of them. And it is unclear at the moment how to fix them. Maybe renormalization methods work. And moreover, it has the consequence that the GNS Hilbert space is a non-separable Hilbert space. So maybe there are way too many state vectors. So there are maybe super selection rules and so on. So also this is not very much under control. Next, of course, the Hamiltonian is very complicated. So in order to say something about quantum locality, as I would try to advertise. Is something very hard to compute. It would be nice to have calculational tools at one's disposal in order to check this idea, but that has not been done yet. In general, it would be nice to make contacts to quantum field theory in curved spacetime, maybe along the lines that I said, that you have some semi-classical excitation of the GNS vacuum, which is sufficiently stable for a long time in order to see that you get the correspondence with respect to a quantum field on a spacetime which is very little fluctuating about a given classical background. And in order to achieve this stability, maybe ideas from decoherence are necessary, but also this has not been worked out yet. And with this, I end my talk, and thank you for your attention.